when I saw John Gilbert's title of his talk, that was actually going to be my title of my talk before I wrote something down. I'm like, well, I can't do that. Both probably influenced by J.R.R. Tolkien or The Hobbit or something like that. Not to embarrass John further, I wrote this abstract and sent it out, and I was very happy with it. But then I thought, well, this is Alan's birthday party. Should I do something more extemporaneous and just fill it with Alan anecdotes? And I asked John about that, and John, who's been a tremendous mentor of me and has witnessed many of my extemporaneous performances, waited a couple days and in his very gentle way just said, I really like your abstract. It sounds great. So, so we'll refrain a little bit on perhaps some more extemporaneous stories and stuff.
I would have given you the title. It would have been okay.
So just very pleased to be here today. And I think most of us have begun with a few remarks on some of the philosophical influences. And for me, one of the, I've worked with Alan very closely for the last couple of decades on such a wide range of topics, which has really been a tremendous pleasure. And I especially, and Alan is not alone amongst his peers here that work, that are well known in so many communities, which is just really tremendous. And to me, I think one of the ideas, if I had to sort of reflect, that has really sort of resonated is, there's this concept in mathematics that I think we all know of, elegance, right? Which we sort of really hold in high regard. I think people in other fields don't really necessarily understand it as much. I'd say in physics we have it in terms of the elegant experiment is always something that people strive for. And I think that the concept that, we all know that the elegant math or the elegant code often provides insight. And from my perspective, I think one of the deeper ideas that Alan had is but it should also be faster. And I think to me that's one of the essence of Julia, is that you can write both the elegant code, and if you write it the elegant way, it should also give you more performance as well. And I won't, there's reasons for that. And so I found that, and that's something that sort of certainly has spilled into all the work I've done over the years. And I'm very grateful for Alan to do that. And in terms of what I do, I think sometimes people don't know, right? I'm a fellow out at Lincoln Laboratory, and sometimes people are like, well, what do people in the federal labs do? And I think two things that we do that are really relevant here is, one, we try and understand the really important problems that are happening, whether it be pandemics or how to protect computer networks or other types of things, understand these hard technical problems and work on them, and often take ideas that are developed in academia and figure out how to make them practical to advance these really hard problems. But another thing we do is we kind of have to recognize that those ideas don't come in a vacuum. And we need to help folks understand which areas in academia to grow. And so we do a lot of what we call exploratory research. We talk to people like yourself, like Alan, be like, what are the ideas that are happening? What are the new areas that are coming? And we'll then often run and do some exploratory research to see, would this benefit, is there any potential of this benefiting a practical problem? And if that's the case, then we can go to folks and say, you should go give these people a lot of money, right? And then they go and do that, and then the ideas mature over 5 or 10 years, and then we can figure out how to do that. And so a lot of the work I want to show you is a result of that exploratory research, a lot of conversations with Alan and other people themselves. And of course, this is not in a vacuum. I mean, many co-authors over the years, for those of you who are not, and this is just within the sparse space and stuff, working at Federal Lab, you get to work on a lot of diverse areas, right? So that's really a lot of fun. So I'm just going to this is my outline. Of course, we always have outlines in our talks, but I'm just going to talk about a few topics here. And to get directly to the title, and it was somewhat said in tongue-in-cheek, and this is sort of, if you subscribe to the thought that all things are just matrices in the end, which I think there's some people who subscribe to that thought here, then we do allow some separation or differentiation amongst that area between what we call dense and sparse and hypersparse. And these are sort of crude, sort of lay definitions of what those are. There's a paper here that many of you who are in this room wrote that really give a much more rigorous definition of what these different categories of dense and sparse and hypersparse are. I will say in my own career, I started very much in the middle, which is this sparse case, because that's where and I've now sort of clearly gravitated to the two extremes. I would say for you that the dense world, for those of you concerned about Moore's law, if you're interested in it's alive and well as long as you're interested in doing variable precision matrix multiplies. The next generation hardware is extraordinary. You can get processors that will do 3 petaflops on a single chip if you're willing to do variable precision matrix multiplies, which of course is driving neural networks. And then on the flip side, we've kind of almost a lot of our work has moved from this traditional sparse place to this hypersparse place, where which and mostly due to Tim Davis's work, who just put that as an Easter egg in some of his software, and then we had it, and now it's everything we do. So, and he wasn't even told to do that. He just decided, I can do this now. So this, I'm mostly going to be talking about probably stuff in that hypersparse regime. And it would be remiss for me not to plug my own book, or John's book, this was really a starting point for a lot of our ideas. And which is this central sort of, it's almost the logo of this graph algorithms and matrices world, which just shows up there the duality between breadth first search and vector matrix multiply. I would say the only thing that's changed is I've now become a left multiply person rather than a right multiply person. Well, I'll say this, it is a lot easier to treat matrix multiply with rows than it is, there's no room to go to the matrices. You're just stuck in vector land, and so we're doing matrices a lot. So, but yes, that is, we have, and then, so that is one thing there. But this was only a starting point. And, what was exciting is we completed that book in 2011, and we had a chapter of what is next. And I was fortunate enough to have some very wonderful co-authors, many of them shown here, that talked about what are the big questions that, we've done this work, what are the big questions that are next? And, we sort of put them in these 5 categories, sort of ontology, time evolution or dynamics, detection theory, just like how do you find things in graphs, algorithm scaling, computer architecture. And so I'm just going to sort of give people a little tour of a lot of the exploratory research that we have done that has set the stage for many research programs that have supported many folks over the next, over the subsequent decade. Obviously, I don't think you need to motivate this, that networks and graphs are really important. They're everywhere. Many wonderful books. And neural networks, by the way, are graphs, right? They are networks, they are graphs, and they fall well into this scope. And so I think there's no limit of the motivations for that. And so I'm just going to kind of go over some of these topics here. In terms of, algorithm scaling in what we typically mean is if you add computing resources, do things speed up? If you make problems bigger, do they scale in the way that you want? Do they not just sort of fall off a cliff? If you make problems more complex, is the complexity sort of managed in a consistent way? And, being at a federal lab, a lot of our job is measuring, coming up with ways to measure the progress that's going on there. And, one of the big tools we use is this thing called Craft Challenge that we put together. And, this, just gave us a way to look at how good different tools and technologies in the graph space were here. And the important thing that we discovered was that even though folks were using phenomenally different tools, and even different underlying processors, they were all getting the same performance. The good implementations were all getting the same performance because it was just memory bandwidth limited. And so since everyone had the same memory chips, it was memory bandwidth limited. And so the challenge then became, well, if that performance is now generally achievable, how do we make that available to everybody? How do we raise all the boats, right? Not just make this a performance available to the very best, but how do we move the whole field forward? And that's when many of us came together. And on the long journey, and again, something you get to do at the federal labs is really develop standards. And so this was a paper that we published in 2013, and Tim Matson Intel really led the drive there. But you can just read it. It is our view that the state of art in constructing large collection of graph algorithms in terms of linear algebraic operations have been mature enough support emergence of standard primitive building blocks. It sounds like, the Declaration of Independence, right? We hold these truths to be self-evident, basically. And I think one of the really exciting things about it, right, is we sort of really brought this concept that, John was a big instigator of. I'd never heard of a semi-ring in my entire life. I just sort of one day in an office a couple blocks from here, I said, hey, I did this thing and this graph problem, and this thing sort of looks like a matrix multiply. Is that a thing? And he says, yeah, that's a thing. It's called a semi-ring. And so, up at the top there, for you who don't know, we have this sort of odd notation, this plus dot times notation, which I think you can almost actually even do in Julia. I'm not sure, but very close to it. It is APL notation, yes. So it is APL notation, right? Which is the kind of the language of all of these things, right? And including its own unusual runic fonts. But at the top is the conventional arithmetic matrix multiply. That just says I'm going to do a bunch of element y multiplications, and then combine. It's essentially how I do my dot products. And it just turns out you can do a lot of different dot products that way. And they all support different types of really important problems. And so this standard had, in addition to be able to really support sparse matrix math, and it's been called the Graph-BLAS now is what it is, in addition to supporting matrix-matrix multiplies really well, it also fully supports all of these things, which has allowed us to explore a wide range of things. Perhaps one of the most interesting is neural networks. So there's the standard neural network. We've all seen these many times, right? I have features going in, I do a bunch of matrix multiplies and thresholds to get outputs to determine if something is a cat or a dog or whatever, right? And that's the equation up there. That is the standard sort of iterative DNN equation. And the H function, which is often just something we call the rectified linear unit, which I think is a very wonderful way that we sometimes do of giving very long names to the simplest possible nonlinear function you could imagine, right? Which is just, if it's above 0, don't do anything. If it's 0 or less, just make it 0, right? I mean, it'd be difficult to come up with a simpler function, right? You could accidentally implement that by just wiring things wrong, and it would give you the rectified linear unit. And maybe that's how they discovered it, right? So obviously, we need to have a nonlinearity. I mean, this is often a question we give to students. If I didn't have the nonlinear, what would happen? It's like, oh, well, actually, you can just roll this all up into one equation, and we can use the same math that we all know and love. But what's interesting is if you look at these two things and combine them, you can actually recognize that you're actually oscillating between two of these semi-rings, which is very cool. And I actually think it's an interesting area too. That is, in a sense, the system is linear, but you're sort of bouncing back and forth between the standard arithmetic semi-ring, which you're doing for the weight computation, versus something called the max plus semi-ring, which is sometimes called tropical algebra or geometry, and there's a whole bunch of mythological stories about the name of that. At this point, none of which we even know are true, but they make for great, you can look them up, and at this point, people don't know if they're true, but it's fun. It's something to do with Brazil, I guess. So, likewise, another big area that you may have heard about, and that we're very interested in, is called graph neural networks. And sometimes I think this, and again, I can never do justice to this the way Michael Bronstein is, and so I literally just stole a slide from his talk, and I strongly encourage you to see Michael Bronstein's video on this. But it's essentially, a neural network essentially takes in features. Well, what if I want to do a graph? What if I want to do some kind of categorization of graph? Well, it basically takes two sets of features. It says, compute a bunch of things on every node or edge of the graph, this typical type of statistics we might compute, whatever they are, and we'll just create a whole list of those as features. And then, just as in images where we do convolution to sort of bring together local pixels, you can also pass in the adjacency matrix as your rule for bringing together local pixels. It's literally just that. And then you can do neural networks as ways to categorize things. I would argue that, as in many things now with DNNs, this may mathematically be a less efficient way to actually do the problem. However, if my computer is able to do these operations 100,000 times more efficiency per watt, Even if my algorithm is 10 times worse, I'm still winning by a factor of 10,000. And I'd say that is a reason why. I mean, you know, if I do this with conventional math and I'm getting, 10 megaflops on my single core processor, I'm feeling pretty good. And if I have a 3 petaflop processor that I can also buy for the same energy consumption, you can see how those numbers work out. So a lot of times I think it's just we have a new 2x4 in mathematics, right? You can still go cut down trees and build a house that way, but you know the 2x4s are really cheap and they're everywhere, and so even if the 2x4 isn't the right thing, it is good. So let me sort of move on here and talk about sort of ontology and schema. Another area that was very interesting and sort of opened up to us was the concept of, well, and especially once we got to these semi-rings and we start dealing with sort of non-numeric data, because things like max and union and intersection all work on non-numeric data, we could start dealing with much more complicated situations. So rather than having a graph that is a bunch of indices that sort of describe the situation, we actually could have the row labels and the values be strings and do matrix type operations on them. And we call this associative arrays, and we wrote a whole book on it. And it really allows you to bring together 3 completely different important ways of viewing data, which I will cover here, which is essentially different types of operations we do in databases, whether it be SQL, whether they do NoSQL. So SQL, like if you buy something on the internet, how many people have bought something on the internet? Okay, you've used an SQL database. All right, good for you, John. Off grid, man, stay that way, right? If you've ever done an internet search, you've used a NoSQL database. The entire back end of internet search is these NoSQL databases. And modern analytic databases, like the thing that computes your payroll, are these NewSQL databases. They're designed for doing analytics. And they all have very different mathematical underpinnings, but they are all sort of unified by this associative array representation. And you can see that everything they do is just 5 operations, right? This is why SQL databases work. It is literally just the semi-ring over the union, it's the union intersection semi-ring, which is why they can do what's called query planning, because it's a linear operator and they can sort of in advance say, okay, is this going to work and how do I rearrange operations and know that it doesn't change the results, which is essentially what we do in linear algebra every day. And that's essentially why they work. So again, enough about me, more about my book. So this got us to, we wrote this book, you can get it at MIT Press, and we really formalized the mathematics of what these associative arrays are. They're essentially mappings between, finite strict totally ordered sets, over a value set, which is a semi-ring, and you bring them together with, properties from semi-algebras and stuff like that. And so a lot of, and again, sort of going back to this, this theory to practice to theory thing. Another really important problem that people became interested in, and when we started in the world, in the matrix, in the Gala book, we were really talking a lot about adjacency matrices. And everyone loves adjacency matrices, and people show them all the time. But I actually never use them. They're not actually that useful in practice. They're useful as a final result oftentimes, but almost always the data we get is better handled with something we call an incidence matrix, which is where every single row is every single edge is a row, and then all the different vertices, and here I've separated them, but usually we just smash them together in one big giant table, where every single column is a vertex. And so you think about if I get a record that's coming in, that's just a row, and I just keep adding these rows, and then I can encompass a much more diverse set of graphs than I could otherwise do. For instance, the adjacency matrix can essentially handle, directed weighted graphs. This can handle directed weighted multi-hypergraphs. And most of the data we see in the world tends to be multi and hyper, right? It allows you to differentiate the thing of me having this communication with all of you, which is essentially a hyper edge, right? versus me having a bunch of individual communications. An adjacency matrix can't tell the difference between those two situations, and they are very different and very important. And so this is why we do this. And so people ask, like, well, how do you do streaming and how do you do stuff in these matrix things? Like, well, it's really simple. It's still just matrix math, the same thing. GraphBLAS could do this without any modification whatsoever, and we always knew that. We're just now having to teach people these ideas. And this then naturally leads into databases. We've set the world records in database performance using these ideas. The most powerful open source database thing is a database called Accumulo, and we actually work the developers. It has an entire matrix graph engine inside it that's sitting like an Easter egg, waiting to be discovered, and so people can do that. More world records using these ideas. One of the great things about hypersparse matrices, and I'll get into I've built a lot of parallel libraries over my life, like about 9 different parallel matrix libraries, right? And they all have the same philosophy, which is take a matrix, come up with some map for chopping them up to create locality on processors. Everyone does stuff, and occasionally they move stuff around, and you can make that elegant to various degrees. But we went to these hypersparse things and associative arrays. The question is, well, the natural thing is, well, we should do that. And then what we realized is that whenever we were building our parallel libraries, it was just a global to local mapping. But when you have hypersparse indices, you don't need to do that. Everyone can have sets of indices that are completely distinct, right? And your combination operation is just addition. So all you have to do is take your data, put it in the same hypersparse space, and just have everyone just do their stuff, and whenever they want to combine an operation, it's like, well, we're just going to add stuff up. It allows you even to divide things up that have the same entries, as long as the operations work over that. So all of our beta-based work in this, different processors get data, they work on their thing, and then you say, all right, just everyone add up everything now, right? And so it's been, so we've actually never needed to build parallel explicit structures for any of our hypersparse work. It just works. I just know, like, okay, as long as the addition still works, which I have, because I'm not dealing this local to global index stuff, which is very exciting. And this has had a lot of impact on applications. Ultimately, we're important, applications. So this is Genome. Have you ever heard of something called BLAST? This is BLAST implemented in 1 line of code. With GraphBLAS, it will be faster than anything else. There's other biological implications. In certain countries, if you go to the pharmacy and they do your drug interaction check, it's being done with this technology, which is great because actually kind of scary. It turns out that's like 30% of emergency room visits are drug interaction. And mostly the checking is the pharmacist right there at the point of sale. Do they happen to look at it and read it and sort of notice stuff? And we can do customized checking with this technology.
By the way, BLAST was written by a graduate student who was in applied math when I don't know.
Yes. And so it's one of the most tremendously popular things. One of the things that's been very important is privacy, especially as we deal with the internet. One of the big problems with making the internet safer is that in order to make it safer, we have to share data. But we can't do that because of privacy. Well, it turns out that with matrices, where the math doesn't change if you permute things, this gives us a form of privacy that actually most lawyers will sign off on pretty easily, and meets things like GDPR and other types of requirements. And so we created this method, like if you have network records like that, just source and destination IP, we put them into this sort of hypersparse associative array there at the top, and then we can just anonymize it through a variety of methods. And we can still do the exact same equations on it. Everything works just fine. There's nothing that changes, and we just de-anonymize the result appropriately as needed, And so that's been a very effective thing. And of course, coming back to graph neural networks, this is doing these kind of ideas. Well, we can now just take an entire image of the entire internet, all anonymized, and then run it through graph neural networks to find, interesting phenomenon. And one of the, getting back to the random matrix thing, and this is something that Alan knows I've talked about, is that, and we've found that heavy tail distributions are utterly universal in almost all data that has anything to do with humans or the internet. right? And so this is something that, like, at this point when we have, work on the largest publicly available data sets of this type with trillions of entries, and this is, if we don't see this, we think there's something wrong with the sensor at this point. It's like the normal distribution would be in a physical setting. And this is just a simple, so this is just whatever your quantity is, say how many messages you received, and it's just a histogram of them. And then there are, on the right would be, say, Google, it talks to everybody, and then on the left is us, we talk to nobody, right, effectively, right? Certainly by Instagram standards, we talk to nobody, right? Well, in fact, we would be at the zero, right? So, like, just not even on this. But, so we've seen this to be universal, and so unfortunately, heavy tail distributions like this have some very annoying problems, like not obeying the central limit theorem. Which is a core assumption, and essentially almost all traditional statistical methods that we have collapse pretty quickly. But it's a very exciting area. So with that, I think I'm at the end of the time. I think you made up some time, but very much appreciate that. Sparsity, really awesome stuff. We've got a lot of math that's been developed. And if you like these ideas, let me plug our conference, which is virtual. And we have we're now the largest performance engineering conference by content in the world. It's virtual, it's effectively free, and I just analyzed the other day. I went back and looked at papers, that were over 10 years old, and the things that our first GPU talk, and we've had hundreds since then, was 2004, right? Our first quantum talk was like 2010, right? And having run this conference so many years, I remember the conversations about those papers, and they were not slam dunks at all. And it just goes to show that innovation requires people it never looks great when it's first born. And you need venues like this that can be that place. And I'm thinking, we were certainly one of the first venues for Julia and many of work. And when stuff is not quite just that slam dunk, ready for science or nature type of thing, it needs a home to grow and develop. And so we've been years ahead. And so I encourage people to participate because the next Julia, of course there won't, but the next Julia is probably being presented at our conference, 10 years ahead. Yes, there'll be a next something, yes. So thank you very much. I hopefully you at least found that entertaining.
Any questions or comments?
Stunned.
All right, Jeremy, that was great. I don't know why I ever bothered to give a talk at a conference that you're speaking at, but I have a really nerdy point to make, which is you talk about incidence matrices as opposed to adjacency matrices, and I couldn't agree more. And I once tried to put together a talk about you want algorithms on a sparse matrix A transpose A, but you've only got A. And there's an amazing amount of work on that out there, which nobody ever tries to unify or think about together or anything. I think it's still, I'd love it if somebody would write a survey paper, and I'm too lazy.
Well, just to nerd out at that, so our sort of fundamental equation that it's like the voltage equation in electrical engineering is essentially what we call E transpose E equals A. Oops, broke the chalk. Right, so this is the adjacency matrix, those are those things. And so we just find ourselves constantly going back and forth between this. So we work in this land, and then when we want to put the final result often will be something that looks in this land. And we're just sort of bouncing back and forth between these two a lot. And I think that just directly ties into what you just said, that there's a lot of, and we have students who are actually beginning to explore this, right? That, okay, let's go and rewrite all our adjacency algorithms in terms of incidence matrix algorithms, and then see, what properties we can exploit. So.
There are lots of things you can do that are randomized than deterministic. You can do well deterministically on A, you can do randomly on B.
Well, that would be great. So please email me some of that results. We have students working on it right now, and they're probably wandering in the dark.
Yeah, I mean,
So.
you have like a fundamental proposition of numerical algebra to always work on the the E and not the A in a more, even more general sense?
Sure. We were all taught to form, not to form mineral equations, right? Right.
The voltage domain in signal processing.
Yes, right, yes. Steve understands my analogy right over at Lincoln. We always talk about this, but yeah. So E is the voltage, A is the power, but you know it's
Go with the middle matrix between the two.
yes, yes. So ours is just a diagonal there, right, or whatever, something like that. So, yep. Oh,
I think
we need to move on. Yeah, I guess. Yes, I've already. Yes.